Dear authors and invited guests, welcome to the technical session 7C. Myself Siddhi Audi, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastics LLP, it is my great pleasure to welcome you all to the 10th International Conference on Information and Communication Technology for Competitive Strategies, ITCCS 2025. The 10th edition of the conference is being held organized in a hybrid mode. The physical event was held yesterday in Jaipur, and the virtual event is being held via Zoom meeting on 16th and 17th. I hope you all will enjoy today's interactive and knowledgeable session throughout the day. Now, in this session, in total, we will be having 10 presentations. Each presenter will be given a time span of 10 minutes, 8 minutes for presentation, and 2 minutes for question and answers. On completion of 8 minutes, I will be raising a gentle reminder. There is also another request to all the participants that you all stay connected with us till the closing remarks. If you face any issue or have any technical glitch, you can write it to me in the chat box and we will be helping you. Now, just before we start with the session, I would like to introduce you all to today's session chair, Dr. Vidya Gaikwad. Dr. Vidya Gaikwad is an assistant professor at Vishwakarma Institute of Technology with over 16 years of academic experience. Her expertise spans cloud IoT security, lightweight cryptography, data visualization, machine learning, and blockchain technologies. She has actively contributed to teaching, research, and technological advancement in her areas of specialization. Welcome, ma'am. Welcome to today's session.
Thank you, Siddhi. Yeah, thanks.
Now, without any further ado, we will get started with the very first presentation. So, the first presenter is Takumi Hattori from Tokyo City University, Japan. And the paper title is A QoS Improvement Method for In-Vehicle Infotainment Systems Considering Intercore Shared Resource Interference in Multi-Core Environments. Sir, please get started with your presentation.
はい、共有のリクエストをしています。
Yes. You can share your screen now.
Thank you. Okay. Hello everyone. My name is Takumi Hattori from Tokyo City University, Japan. Today, I'd like to talk about improving QoS in automotive computers. First, let me explain the background of this study. In recent years, there has been a growing demand in the automotive industry for in-vehicle infotainment system, IVR system that can provide both vehicle-related information and entertainment service such as video and audio streaming. At the same time, with continuous technological advancement in automobiles, there is a strong trend toward integrating in-vehicle networks. Figure 1 shows how in-vehicle networks are gradually integrated, first by domains and then by zones. This integration aims to reduce beacon weight, lower manufacturing costs, and simplify complex wiring. As a result, modern vehicles require systems that can support large volume communication and processing with real-time guarantees, where information-related function and control function coexist on the same communication infrastructure and embedded computing platform. As-Real Network, a real-time in-vehicle streaming system based on TMO. In this system, a distributed processing middleware running on Linux is used as the execution engine of TMO. It enables real-time display of the vehicle status transmitted from ECU over CAN, together with video streaming sent from an Ethernet camera device. However, because it relies on time-trigger execution, all nodes must be time synchronized, and variation in communication latency cannot be tolerated. As a result, the applicability of this approach is limited. Another relevant study is a time-trigger distributed computing environment based on physical time and logical time. This work aims to tolerate variation in communication latency within distributed system by adapting a time-triggered architecture based on logical time. By using logical time, it allows a certain degree of communication delay variation and eliminates the need for global clock synchronization among nodes. However, this approach still faces challenges when being applied directly to environment where control-related and information-related tasks coexist. Therefore, in this study, I aim to enable the transmission and reception of information system messages, such as video data, on the same computing platform and the same networks without neglecting the QoS of control system data, such as vehicle status. First, in this study, we reproduced an in-vehicle infotainment system using the distributed processing environment mentioned earlier, and we treated this as our target system. Figure 4 shows an overview of the target system. This system assumes an in-vehicle scenario where both vehicle status information and video data are handled. It consists of two embedded computers intended for automotive use, referred to as Node 1 and Node 2, and video streaming server. For the embedded automotive computers used as Node 1 and Node 2, we employ development boards equipped with Renesas Automotive SoC, the Arca H3. Three computers are connected via Ethernet through a router. Between Node 1 and Node 2, vehicle status messages are transmitted and received, while video data is sent from the streaming server to Node 2. Next, to identify the issues that need to be addressed in this study, we conduct an impact evaluation experiment as shown in Figure 6. In this experiment, we operate the target system while sending three types of messages that emulate vehicle status data and simultaneously streams video data from the video server to observe its impact on QoS. As a result, we found that the QoS of the control system messages was significantly reduced to an unexpectable level. Specifically, the round-trip time of messages exceeded 2 milliseconds on average, and the worst-case latency was more than 20 milliseconds. To reduce the number of core reallocation and thereby decrease the number of context switches, we proposed method 1, in which the control system processing on Node 2 is pinning to a specified CPU core. We implemented this method in the real-time simulator on Node 2 using Linux system calls. When we conducted experiments under the same condition as the impact evaluation, the round-trip time messages was significantly reduced down to a level that is acceptable for practical use. Next, in this study, we focused on resources that are shared across CPU cores in multi-core environments such as cache memory. In multi-core environment, when multiple CPU cores attempt to access shared resources simultaneously, interference can occur within those resources, potentially causing processing delays. However, approach like method 1, which simply increase to decrease the number of the available cores, do not take into account interference among threads within these shared resources. To address this limitation, we extended the real-time simulator used in method 1 and added a co-allocation mechanism that considers shared resources interference among CPU cores. We refer to this extended version as method 2. In this mechanism, core on the Alka H3 platform are grouped based on their shared level 2 cache, meaning that each group consists of cores sharing the same level 2 cache memory. Thread allocation is then performed within each group. As shown in the example in figure 8, the real-time simulator occupies core 0 and 1 in group 0, and the threads generated by the real-time simulator are assigned to core 0 within the same group. To evaluate the effectiveness of method 2, we implemented the method and conducted an experiment computing it with method 1. The experimental setup was the same as before. However, to obtain more accurate measurement, we fixed the video receiving and playback process to the third and fourth core among the 4 available cores. Under this condition, we ran the real-time simulator implementing method 1 and method 2 measured the processing time of message ABC on node 2. The initial result showed that the average processing time of this message was significantly reduced with method 2. Although we haven't yet accumulated enough tries to draw a definitive conclusion, one possible reason why the worst case latency didn't improve as much is that the real-time simulator performs co-allocation processing at startup, which may introduce delays. Here is the conclusion of this presentation. That's all I want to say. Thank you for listening.
Yeah, it's really a good work. Can you tell me what popular informant platforms are used in vehicles?
何が一番有名か。そうそう。緊急内容で一番。
研究内容で一番有名。
Can I repeat the question?
一番有名な、その搭載されている中で一番有名な IVA だっけ。
Okay, thank you for question. Most.
Okay. Can you tell me the difference between informant and telematic systems?
違いでニューメリカルアナリシスでだから違う今まで従来の違うものと違う。
Okay, thank you. And yes, and my method is so my method goals is on the same computer and networks trans- and transmit and receive information system message and control system data. And なんだなんていうの従来の
For example of the
Yes, and old IBM system is the not same computer and network, but my method is use the same computer.
Okay, fine,
Okay,
fine. Yeah,
thank
okay.
you.
Yeah, thank you.
Thank you, ma'am. Thank you, sir. Now we will go on to the next presentation.
Thank you.
Next,
Evening.
the next presenter is Bindya Venugopal from Savitha University, and the paper title is A Trust-Aware Federated Blockchain Framework for End-to-End Security in IoT Networks. Ma'am, please start with your presentation. I think she is not joined the meet yet, so we will go on to the next presentation. Yes, ma'am.
Ma'am, there's a little network issue. Shall I join after the next participant?
Yes, sure, you can do that. Meanwhile, we will go on to the next presenter. So the next
Okay.
presenter is Narayani Pohokar from Vishwakarma Institute of Technology, and the paper title is Automatic Rain Sensing Car Wiper. Ma'am, you can
Excuse me, ma'am.
start with you. Yes.
Ma'am, I'm Ranjana. I do not have this performer of the uh, conference.
Ma'am, I don't know. What are you trying to say?
Actually, you have आपके पास ये सारी पहले से ही है.
Yes, ma'am, we have a list of presenters, and
अच्छा.
your name is on the seventh number.
Okay.
Yes, so you're there in this conference. Okay, if Narayani has joined, ma'am, any of the co-authors or authors present, please start with this presentation.
Okay, ma'am.
Okay, I'll stop sharing my screen, ma'am. You can start.
Okay. Good morning, everybody. I am Narayani Pohokar from Vishwakarma Institute of Technology, Pune, and I am the presenter for the today's topic, automatic rain sensing car wiper. So, these are the people that I have worked with, respected Professor Sachin Sawant sir, respected Ma'am Aarti Bang ma'am, and my colleagues Sneha Narnavar, Vedant Nangre, and Nayan Jain. So, coming to the topic, that is automatic rain sensing wiper. Starting with the today's introduction. So, basically, we have developed a system. As we know that today's there is a risk and number of accidents are increasing day by day. Usually, the wipers which we are using normally are manual wipers, and they need to be operated manually. They are traditional wipers. So adjusting the wipers at every time is very disturbing for the driver. So we have developed a system that will automatically sense the rain and will start rotating the wiper. Luxurious cars are having this type of facility, while normal cars are still struggling for this facility. So we have developed a cost-effective system for this. Coming to the problem statement, have you ever wondered what if we replace a manual wiper with the automatic ones? What happens if the manual wiper is replaced with automatic. An automatic rain sensing car wiper can use to detect the presence and intensity of the rain based on the intensity. This system aims to improve driver safety, comfort, as well as convenience by minimizing driver intervention and ensuring clear visibility under changing weather conditions. Coming to the objectives of developing this system can be automatic. It can detect rain and start the windshield wiper automatically. It removes driver intervention. Uh, it is based on the wiping speed is based on the intensity. As the existing wipers are fully manual or semi automatic, it requires continuous and constant driver attention that distracts the driver. So this system is perfectly for that purpose. Coming to the working part, as we can say, when the rain droplets falls on the windshield wiper, the sensor senses the droplets. It then transforms the data to the Arduino Uno microcontroller. The Arduino Uno then processes the data and it then transfers the data to the servo motor, and the servo motor will work according to the intensity of the uh, rain droplets, and it will rotate automatically. This is how simply this system works. Coming to the literature review. Uh, so a fairly good amount of work has been done on this topic, and a lot of authors have wrote papers on this. Coming to the first paper, that the author has studied about the rain, snow, hail, and the adverse weather conditions of how this system will help the drivers to travel in those blur scenes. The second author has proposed that how AI can replace the traditional methods through sensors. Vijaya Lakshmi ma'am has also worked and they have designed the automatic rainfall detection and wiper system. They have focused on improving both driver safety as well as driver's convenience. The fourth author has focused on how cost effective this system can be. Uh, One of the earliest works of Terrakura have developed a paper based on automatic rain sensing car wipers as the emerging need for the safety. The other authors, that is Alazavi and Chakravarti, have introduced a automatic rain sensitive windshield wiper system, which is according to the changing environmental conditions. So this was about all the literature reviews. Coming to the advantages, we can say that this system will improve driver safety as well as reduce the distractions. It will be efficient and reliable for operations. It can be low cost, and its implementation of the system can be done in normal cars. That will also be profitable for normal peoples. This can be used in cars, automobiles, smart vehicles, as well as autonomous driving systems. These are the results of the experiment that we have done. Coming to the conclusion part, uh, this automatic rain sensing wiper system successfully demonstrates how sensor based automation can improve driving safety and comfort. By automatically detecting rain and adjusting the wiper operation according to rainfall intensity, the system reduces driver distraction and ensures clear visibility in changing weather conditions. This is the video of the working model. This shows how the sensor detects the rain and starts rotating the wiper. Thank you. That's all from my side.
Yeah, very ultimate work. And you have solved one real life problem. That's good. Good to see your implementation also. Yeah. Can you tell me what will be the effect of temperature on your rain sensors?
Ma'am, we have not worked on that part yet, but we will surely try to solve that problem.
Okay. So how you're going to measure the sensor calibration? That means how you're going to measure the accuracy of the sensor?
Yes, ma'am.
How you're going to measure the sensor calibration?
Um, Ma'am, we have actually used rain sensors for that. Uh, they will uh, detect the rain, and the microcontroller will work on that, I guess.
Okay. Okay. Thank you. Yeah.
Thank you.
Thank you, ma'am, for your presentation. Now we will move on to the next presenter. So the next presenter is Asha Dige from SCTS Pune Institute of Computer Technology, and the paper title is Decoupling Geometric Normalization and Feature Extraction, a two-stage system for robust palm print verification. Ma'am, you may start with your presentation now.
Yes, ma'am. Is it visible, ma'am?
Yes, ma'am.
Good morning, everyone. My name is Asha Dige. I am a research scholar from Department of Electronics and Telecommunication from PICT Pune. So, my today's topic is decoupling geometric normalization and feature extraction, a two-stage system for robust palm print verification. Uh, these are the contents. So in this, we have to see the introduction, the literature work, what the data is used in this, the baseline architectures that I have used to work for the further system, then two-stage verification system, results, and the workflow of my work. So we will start with the first introduction. Now, what is mean by biometrics? That my work is related on the biometrics. Normally, biometrics is nothing but in today's digital world, we want a secure and easy user authentication. So it is very important. So if we consider the traditional security methods, for example, password or ID cards, which we know or what the user know or carries, which are forgotten or stolen or misused by the thief or any person. So this biometric recognition offers a better solution by using the or identify people by using unique physical and behavioral characteristics, for example, fingerprint, iris, or facial features. So the need of biometric security is to secure reliable and convenient authentication, and we can less dependent on the passwords and tokens or anything that the user carry. And biometrics offers a strong alternative using unique human trace. So I choose here the palm print recognition because this is the emerging modality beyond the fingerprint, iris, and face. Because the palm print acquires a whole palm. So it consists of large surface area which has a rich features, that is lines, wrinkles, and ridges. So it is very useful for the high security applications. So I selected for the palm print recognition. Then this is the hand geometry and palm characteristics that I have used. So hand geometry is nothing but the geometry or the parts that pump consist of. And what are the characteristics of that? It consists of principal lines or wrinkles or creases that we can work on that particular parts by using the different deep learning or machine learning approaches. So these are the advantages of the palm print verification. Now, in this first is the high distinctiveness. So it contains rich line, wrinkle, and textual patterns that uniquely differentiate individual human from one to another. Now, next is the high permanence. The features of the palm print consist of largely unchanged over time because the palm is very unique, so it cannot be changed over time. Next is the high performance of the palm print verification, then low resolution imaging. Because low resolution imaging is nothing but the reliable recognition that can be achieved even with low resolution imaging devices. It is also user friendly and it is highly stable because the palm print characteristics are resilient to minor poses or pressure or illumination variations. For example, due to the brightness, the iris characteristics can changes, or face also can changes due to aging parameters. So it is highly stable. And this is the evolution of palm print recognition. Evolution means I can see it as a related work because from previous very long years, the work on the biometric is continuous. And in the traditional methods, that means in the pre-2015, the work is done on the handcrafted images, which uses Gabber filters or local binary filters. So after that, the end-to-end deep learning is considered, in which the CNN is used for the data augmentation. And after that, the alignment-aware methods. Alignment-aware methods means what the key point detections or the work on the complete minute features are done. So identified this gap, or we can say there is a lot of work on the traditional methods, or we can say there are different works which are done in the CNN, but there are some particular drawbacks of that work, which are nothing but the not up to that is work on the alignment and recognition. That means we are dividing our part into two, so we can work on the each and every minor features of the palm print. So by identifying this graph, my work is going in the two stage or divided into two stage. That is palm print. That means decoupling of geometric visualization and feature extraction. So there are the two states. That is stage one, that is geometric alignment, and stage two is identity recognition. So we can use this palm print recognition to identify the person. So this is the data set evaluation. Data set evaluation means what the data which I use. I use the NIR palm print images, and each here the 100 classes are used. That means each class has a approximate 12 palm print images, and the pre-processing work on the image is done. Here the three baselines are used for the model 1 and 3. The image is resized to 2 to 4 into 2 to 4. That is the image matrix, and the model 2 is resized to 128 into 128, and the channel height handling is also there. For model 1 and 3 need 3 input channels. That means the color images are used, or in the model 2 only one channel is used, that is the grayscale images, and the normalization is also different for first model 1 and 3, and for model 2 the normalization is different. So we will go with the baseline architectures. Here, the first baseline architecture is ResNet 18. This is the standard deep learning architecture, which is pretend on the ImageNet dataset. So instead of using entire network from the scratch, here I use the selective fine-tuning strategy. So here we frozen the first three layers, because the layers learn basic visual characteristics or features, that, for example, edges and textures from the print images. So we only allow final layer, that is layer 4, to train to the network. And the classifier head consists of the linear layer. So here the classifier first reduces here, the classifier must reduce the feature dimension to 512 to 256, and using a linear network, that is RU-LU activation layer. And here the dropout is 0.6, and the final layer consists of 256 to 100. So the model was trained for a 50 epochs. And here the softmax function is used to convert the output into the class probabilities. So here, this is the first baseline architecture, and these are the results for the baseline architectures. Here, we can use the accuracy, F1 score, and log loss for the model evaluation parameters. Now, the second is the DenseNet 121 classifier with direct channel injection. This is also a deep learning approach, we can say. Here, our data is consist of a single channel NIR palm print images, as we see in the data evaluation slide. Here, I modified the network architecture. Instead of converting images to 3 channels. So here, the first convolution layer was replaced with a single channel convolution layer. and the features are reduced to hundreds. So,
Hello, ma'am.
yes,
Ma'am,
yes, no.
we are past the presentation time. Can you please get to the conclusion?
Yes, 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 madam. So this is the just these are the performance baseline architecture. So in that we consider the ResNet 18 is the base performance. So if we consider, I worked on the two-stage verification system. Here I worked on the ROL net and thin plate spline wrapping. And the next is the feature extraction embedding. In this work, if we consider this whole diagram, here I consider the image feature extraction and geometric normalization of component is considered in equally, and the performance parameter of baseline 1, that is ResNet 18 is good. So here we consider the baseline 18. These are the quantitative verification performance of the baseline 1 and the proposed two-stage system. The accuracy for the baseline 1 and the proposed two-stage system is just equal, but by using the baseline 1, we get the accurate results. This is the GUI workflow that I work on the palm print recognition, and this is the demo screenshot. This is also a demo screenshot. So here, instead of using only one baseline, here I used the two-stage architecture, which separates geometric alignment of the palm print recognition from feature instruction to improve the interpretability and robustness of the system. This is the decoupling of geometric normalization and feature extraction for the palm print recognition. Thank you, ma'am.
Thank you, ma'am, for your presentation.
Yeah, Asha ma'am, a very good work. And can you just tell me about how encryption can use to protect the palm print system or
Yes, ma'am.
palm
I
print
didn't get you.
templates?
We can actually, ma'am, this work is only on the authentication. That means we can use this as a security purpose, just like a attendance or attendance monitoring system. If you
Hmm.
want to encrypt the data of the palm print, then you have to use the
Hmm.
different templates.
Hmm.
So we can, that means you have to use the template verification for that. That is another process for the template verification. That means for authentication purpose of the component verifications.
Okay. Thank you, ma'am. Thank you.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you.
Bindiya, ma'am, you can start with your presentation now. You can share your screen directly.
Okay, ma'am. One minute. Ma'am, is it visible?
Yes, it is visible.
Good morning. I'm Bindya Venugopal. I'm a research scholar from Savita School of Engineering. And my paper is a trust-aware federated blockchain framework for end-to-end security in IoT networks. So starting with the introduction, the rapid expansion IoT networks has created major challenge in efficiency and reliability of device-to-device communication. Ensuring robust end-to-end security is essential to protect IoT in diverse and evolving cyber threats. Now, the major challenges in the medical IoT applications where data privacy is not provided, even using modern deep learning techniques for network protection. And also the resource constraints in IoT devices, it motivates decentralized and lightweight communication structures among heterogeneous devices. Then this is my literature survey. I had gone through a lot of papers from different authors, and among that, the 5 main papers were these, and the advantages and disadvantages of each paper have been found in the literature survey. The problem statement is that the IoT growth introduces major security, privacy, and scalability challenges. Existing centralized systems create a single point of failure, and blockchain only or federated learning only solutions lack complete trust, interoperability, and adaptability. device heterogeneity makes trust evaluation and secure coordination difficult. And also the last one was the sensitivity data in IoT is often exposed, reducing privacy procedures. Now moving on to the methodology I used is Trust-Aware Federated Blockchain Framework. It can be abbreviated as TAFBF. And this proposed TAFBF, it integrates multiple security and privacy preserving mechanisms to provide a unified end-to-end protection model for heterogeneous environment. Now, these are the major components to form the TABF. The first one is the thrust evolution mechanism. In the thrust evolution mechanism, each IoT device is continuously monitored based on its behavior, communication patterns, and historical interactions. And also dynamic thrusts are generated using real-time device activities. Malicious, suspicious, or low-thrust devices are automatically isolated or restricted. Now, the second one is the blockchain-based data management. Here, all devices, interactions, thrust score updates, and system events are stored on a tamper-proof blockchain ledger. The third one is the federated learning for secure model training. Here, instead of sending the raw data to a central server, IoT devices locally train machine learning models and send only model updates. Also, the system aggregates these updates using federated averaging process, ensuring data privacy. Now, the fourth component is the smart contract-based access control. The access rules and the policies are encoded into the smart contracts deployed on the blockchain. Smart contracts automate device authentication, authorization, and trust-based permissions. Only high-trust authenticated devices are allowed to participate in critical network operations. And the fifth one is the integrated trust-aware workflow. Here, the systems continuously capture the device actions, compute trust, log activities, and applies federated learning cycles. All the updates are secured via the blockchain. Now, this is the architecture. In the architecture, first we have the input. Here, this is the entry point of framework. All the IoT devices are registered with the system using their identity, metadata, and operational profile. Initial configuration, network parameters, and device capabilities are also recorded. Second block, we have the device monitoring. Once the device is registered, they enter into the continuous monitoring phase. The system tracks device behavior, communication frequency, resource usage, packet exchanges, and interaction patterns. Now, the third block is the thrust score calculation. The monitored behavior is processed to generate a thrust score for each device. Behaviors are characterized as normal, suspicious, or malicious. And the figure here shows the bar graph of a thrust score distributed across the devices. And the devices with low thrust score may be restricted or isolated. The thrust scores are dynamic and they change based on the current behavior. The fourth block we have is the blockchain update. Each significant event, that is the thrust update and abnormal behavior interactions, all becomes a secure immutable block. And all these devices activates and thrust scores are returned into the blockchain. Now we move on to the next block, that is the device prioritization and access control. Using the updated thrust score and blockchain logs, the devices are based on whether they have high thrust, medium thrust, or low thrust. The high thrust receives normal access privilege. Medium thrust, they are restricted access, and low thrust are blocked. And sixth one is the next block is the federated learning aggregation. Here, these updates are aggregated securely to improve global model performance, and this process maintains data privacy. Then we have the smart contract enforcement. The smart contracts encoded into the blockchain automate and removes manual intervention and ensures consistent rule-based security. And we get the final output. The system produces a highly secure, trust-aware IoT network. Now, this is the algorithm. At the first step, we have the inputs, and the inputs are normally the IoT device list, the initial thrust scores, federated learning models, and then moving to the first step, we first initialize the blockchain. Then the devices are being registered, and the continuous loop starts. The second step is to monitor the device behavior, that is to collect the lightweight telemetry and all those. Then we have the compute. We have to compute the thrust score, and after computing the thrust score, we move to the log to the blockchain. There, here what we do is to record the thrust updates and the hashes pointers to interaction logs for immutability and auditability. The next step is the write, trace, and access control. Here, the thrust score is being compared with a threshold value. And if the threshold is greater than or equal to the if the thrust is greater than or equal to the threshold, it will allow a normal participation, or else it is being restricted. Then the next step is the federated learning. In federated learning, the device train local models on device and produce model updates. And then we secure the aggregation, that is a device sent encrypted updates to the aggregator. Next is the update global model. The aggregator produces new global model and optionally distributes it back to the devices. The fifth step we have is the smart contract enforcement. Here, the authenticated devices and get a reward honest contributions or penalize malicious behavior according to the what the results they produce. And this step is being continuously repeated. That is, they continuously monitor that and also recalculate thrust scores. And finally, we get a secure communication, updated thrust score, updated global model, and blockchain ledger. So this is the result. And in the result, I've shown a confusion matrix. In this confusion matrix, we can see that the model is very efficient and with a score of 470 for true positives, that is correctly identified anomalies, and 460 true negatives, that is correctly identified normal traffic. Now, this is a comparison chart with the other security models that exist. We have compared the centralized security, blockchain-based IoT security, federated learning for IoT, and last is my proposed model. From the chart, it is clear that all the...
Sorry for the interruption, but we have
Okay.
passed the presentation time. Can you please get
Okay,
to the
ma'am.
conclusion?
It will complete in 1 minute. The accuracy, anomaly detection rate, privacy preservation, and scalability are high for the TAF-BF. This is a comparison chart for the above table. And to the conclusion, TABF addresses the existing issues using dynamic thrust evaluation, a blockchain for secure immutable data handling, federated learning for privacy preserving models, and smart contracts for automated secure access controls. TABF meets or exceeds standards in accuracy, anomaly detection, privacy preservation, and scalability. These are the references. Thank you.
Yeah, it's really a ultimate work, and you got the results of your work also. Yeah, good to
Thank
see
you.
your work. Yeah.
Thank you.
Yeah, ma'am, there is a hop by hop security and end-to-end security. So
Yeah.
can you tell me the difference between these two?
In hop by hop security, we just have the security between two nodes. That is, in hop, we consider each node, and between two nodes, we have the security. But for the end-to-end, from the destination, means from the source to the destination, we'll be having the security.
Okay. Also, I would like to know, is there any zero trust model for IoT security?
Till now, I haven't got, ma'am. It's not, I can't say it with, means I haven't went through all zero trust security.
Okay. Thank you, ma'am. Thank you.
Okay, thank you, ma'am.
Thank you, ma'am. Now we will go on to the next presenter. So the next presenter is Swapna Nair from Savita University, and the paper title is Dynamic Federated Neuro Swarm Trust Routing for Zero-Day Attack Mitigation in VANETs. Ma'am, you can start with your presentation.
Thank you. Good morning. I am Sapyaji Naya, Research Scholar in Savida School of Engineering. Today, I am here to present my paper, Dynamic Federated Neuroswarm Trust Routing for Zero-Day Attack Mitigation in VANETs. I have arranged my paper, my presentation in this format: introduction, literature survey, proposed model, algorithm, result and discussion, conclusion, and reference. Nowadays, we know vehicular ad hoc networks have played an important role in the smart transportation system and provide safety and efficiency in addition to the interconnected transportation communication. Recent research in minutes focused on advanced detection schemes in machine learning, feature selection ensembles, and deep learning to improve security and identify unknown attacks. Attention-based models also enhances proactive threat prediction, adaptive intrusion detection, and real-time responses in dynamic vehicular environments. Context-aware architectures like Grid V2X and the Intelligent Wireless Security Frameworks strengthen scalability and next-generation V2X protection. Decentralized solutions such as blockchain reduce single point of failure while maintaining data integrity and trust across particular networks. Federated learning and the software SDN-enabled 5G systems integrate privacy-preserving detection and trust assessment to support secure, collaborative, and resilient wireless communication. This is my literature survey. First author Christie et al. Demonstrated that multi-stage intrusion detection with the feature selection ensembles improves identification of known and unknown attacks with cloud-assisted panels. Sarat Rajapat and Deshmukh in 2025 showed that deep learning models effectively detect unfamiliar attacks in IoT-based datasets through intelligent early-stage threat recognition. Lowell in 2025 proved that attention-based predictive modeling with contextual awareness significantly enhances malicious behavior prediction in balance. Suchan, Lakhani, and Kodar 2025 developed adaptive AI-based wireless security mechanisms to strengthen defense against dynamic threats in wireless. Verma et al. In 2024 used the track approach to mitigate DDoS attack in nuclear networks. This is my proposed model. This figure illustrates the workflow of dynamic federated neurosome trust fusion, that is VFN-STR framework. The first step is the system initialization. In this step, initial network parameters and vehicle or node configurations are set. Second step is dynamic trust evaluation. Here, each node continuously evaluates the trustworthiness of its neighbors based on past behavior and communication reliability. Third step is the neurosome intrusion detection. Neural network combined with the swarm intelligence are used to detect intrusions and abnormal activity. The fourth step is federated learning update. Here, local learning models are updated, collaborating without sharing raw data, improving global detection accuracy. The fifth step is trust filter routing decision. Here, the trust case routing paths are selected by considering only highly trusted nodes. The sixth one is feedback from routing and detection result is used to adapt trust scores and models over time. The sixth step is continuous adaptive feedback loop. And the last stage is the aggregator operations. Here, the models are updated from multiple nodes are aggregated to form a robust global model. That is, the framework integrates trust management, intrusion detection, and federated learning to enable secure and adaptive routing. This is my algorithm. Here, DFN-STR introduces a dynamic, trust-aware, and intelligent security architecture for wireless. It computes adaptive trust scores using fast behavior communication reliability, neurosome IDS analysis, real-time traffic patterns to detect zero-day attacks without using predefined signatures. Neurosome IDS also combines neural learning and swarm intelligence to detect anomalous traffic patterns representing zero-day threats. Federated training enables collaborative intrusion model training across vehicles using shared model updates rather than raw data, ensuring privacy preservation. Federated learning enables collaborative model updates across vehicles while ensuring privacy by avoiding raw data sharing. A trust feedback mechanism empowers secure routing decisions, enhancing resilience, scalability, and protection. This is my result in discussion. We have done a comparative review of well-known security mechanism of VANETs under four key vendor performance indicators: zero-day attack detection, trust-based routing, privacy protection, and network dynamic adaptability. We are tested in a realistic VANET simulation with a 50 to 100 nodes and various zero-day attacks, demonstrate strong detection performance, secure routing, privacy protection, and adaptability. And DFNSTR proved that it has the ability to provide a safe, reliable, and highly versatile environment of vehicular communication. This is my test result. Here, I have four categories: zero-day attack detection, trust-based routing, privacy preservation, adaptability to network changes, and detection methods. This compares different security and routing methods based on these five performance matrices. Anomaly-based ideas shows moderate zero-day attack detection and adaptability, but lower test-based routing and higher detection accuracy. Second one, the trust-based routing performance well in trust-based routing, but has lower adaptability and only average zero-day attack detection. Third one, the federated learning ideas improves privacy preservation, adaptability, and reduced detection latency compared to the earlier trust-based routing and anomaly-based ideas. The proposed DFN-STR method achieves the best overall performance with the highest zero-day attack detection, trust-based routing and efficiency, privacy preservation, and adaptability, while also having the lowest detection latency. That is the overall, the proposed DFN-STR method outperforms existing approaches
Hello.
across almost all evaluation
Ma'am,
criteria.
ma'am, we are past the presentation time. Can you please get to the conclusion?
Okay. These are my result in chart form. The DFN STR framework provides a flexible and effective solution for mitigating zero-day attacks in VANETs. It employs dynamic trust assessment to ensure that only reliable and trusted nodes are selected for routing decisions. Neurosum intrusion detection enables real-time identification of suspicious data, patterns, and emerging threats. Federated learning preserves privacy by enabling decentralized model updates without sharing raw vehicular data. As decentralized, scalable, and intelligent architecture, DFN-STR strengthens VANET communication with a rapid threat response and enhanced safety in dynamic environments. These are some of my references, and thank you.
Okay, ma'am, good to see your results and your algorithm. Can you tell me, can we apply machine learning techniques to detect the zero-day attack in VANETs?
Yes, ma'am, we can use machine learning techniques. Machine learning techniques. Machine learning techniques such as feature selection, ensembles, and deep learning is used to improve security and identify risk unknown zero-day attacks.
Okay. Can we use graph-based approach to detect malicious in VANET networks?
Okay, yes, ma'am. We can surely detect using graph methods.
Okay, good, good. Thank you. Thank you.
Thank you. Thank you.
The next presenter is Soham Mehatre from Vishwakarma Institute of Technology, and the paper title is IoT-based smart irrigation and plant disease detection using machine learning. Sir, please start with your presentation.
Hello, am I audible?
Yes.
I'm sorry, but I'm not able to get the option to present my.
Stop sharing my screen. Now you can screen share.
No, I mean, I'm not able to. I can't able. I'm not able to find the option to share the screen. I'm actually present on a mobile. So is it?
Yes, it could be because of that. But from our side, we've given all the permissions, so there is no restriction from our side. Maybe you should go in the Zoom application, and you should like allow all the permissions for screen sharing and everything.
Okay, okay, I'll do that. I'm sorry for the.
Yes, sir, if you need some time, we'll have another presentation in the meanwhile. Then maybe you can join from PC as well, so you'll get some
Yes,
time.
okay, it's okay, it's okay. Yes, thank you.
Okay. So we'll go on to the next presenter. So the next presenter is Ranjana from National Institute of Technology, Kurukshetra. And the paper title is Next Generation Physical Layer Security for 6G Technologies. Ma'am, you can start with your presentation.
Is it visible?
Uh, just a second. Yes, ma'am, it is visible.
Okay. Okay. A very good morning to the respected session chair and all the participants. I'm Ranjana, PhD research scholar in the Department of Electronics and Communication Engineering in NIT Kurukshetra. Today, I'll be presenting my research titled Next Generation Physical Layer Security for 6G Technology, a Study. My paper ID is 298. Here are the contents. Uh, these are the contents of my presentation. Now, then I would like to introduce the overview of 6G. 6G will support extremely fast data transfer, almost zero delay in communication. In it, it uses terahertz waves, which are very high frequency radio waves, to send and receive more data at once. Physical layer directly tackles. Then there is why we need the physical layer. Why we need physical layer? Because it tackles the new kind of security threat accepted in 6G. PLS is not like the traditional cryptography, it secures the data at the signal level. PLS leverages new properties of wireless channels to ensure this secure communication. The properties which we use in it is channel reciprocity, random fading, and spectral diversity. Why expanding security threats in 6G? Why there are threats in 6G? As 6G interconnects diverse uh, devices, IoT nodes, drones, and autonomous vehicles, there is large attack surfaces in it. Increased risk of eavesdropping, jamming, and identity spoofing is there. Now, how the PS enhance the security? Secret generation and reciprocal channels are there. By measuring this channel, both users can independently generate the same secret key without sending it over the air. Artificial noise and cooperative jammings involves intentionally sending random noise signals to interface with eavesdropper. Then beamforming use multi-antenna to focus the signal energy in the specific direction towards the intended receiver. The next is challenges. So there are some challenges in PLS. These are hardware and channel state information limitations. legitimate users becomes equals to the imperfect hardware. Eavesdropper becomes equals to assume perfect hardware. This gives the attacker an advantage where it becomes better in decoding and better in sensing of the signal. The next is high frequencies. As there is high frequencies in it, the channel accurately becomes less. Channel changes rapidly. Too many links must be estimated. Measurements becomes outdated quickly. This lead to poor CSI. So there is weak CSI. If CSI is inaccurate, beams may not point correctly, interference cannot be cancelled, eavesdrop may receive stronger signals, secrecy rate drops. Then security threats in 6G. There are lots of threats in it. That is, the attacker in 6G can use AI powered jamming, directional jammers, smart interference signals in it. Then there is man in middle attack in D2D communication compromises confidentiality and integrity. The hacker can insert themselves between the two devices, that is, read messages, modify it, or impersonate one device. The next is falsified CSI. As a result, the system thinks the channel is different than reality. It transmits secure beam in wrong direction. Attacker receives more signal than expected. This causes low secrecy rate, possible unauthorized access, and degraded system performance. Then next is why. So these are the challenges. To overcome these challenges, we use some technologies. These technologies, first technology is this AI and ML based physical layer security in wireless networks. As I have discussed earlier about the physical layer security, so AI and ML integration makes wireless communication adaptive and intelligent. They help in the system learn from environment in real time, such as changes in signal strength, user movement, and potential attack. Then there is channel prediction, in which deep learning models can predict CSI based on past data, even when the channel changes due to movement or interference. The next is relay and iris selection. Reinforcement learning is used to learn with relays, and iris configuration provides the highest secrecy rate. The best trade-off between good signal to the legitimate user and poor signal to the eavesdropper. Then there is jamming detection and mitigation. Malicious users can attempt to jam or eavesdropper on communication channels. Machine learning classifies, analyze pattern in received signals. Then beam forming optimization. AI algorithm optimize phase shift and beam patterns so that the legitimate receiver gets a stronger, clearer signal. The eavesdropper signal becomes weak and distorted. Then next technology is, then there are some advantages in it. The advantage is it reduces the dependency in cryptography. It is intelligent, adaptive, and data-driven security and real-time decision maker. And future scopes are we can integrate it with edge AI and 6G network. Then there is cooperative jamming in physical layer security. In wireless network, sometimes there is eavesdropper trying to listen to the confidential data being sent from the source to destination. To protect this data, other friendly nodes in the network intentionally and jamming signals send jamming signals. So how it works? The main transmitter sends the data to the user with the help of the node. The node generates the artificial noise, and this noise is very difficult for the eavesdropper to decode the real message. So destination is not affected much. It has multiple antennas, beam forming, and advanced signal processing to cancel or ignore the jamming signal. Eavesdropper receives as a result, eavesdropper receives noisy, useless data.
Hello.
Yes, ma'am.
Ma'am, we are past the presentation time. Can you please get to the conclusion?
Okay. So this is the cooperative jamming. Then there is IRS, is also the technology through which we can reduce the PLS, where it improves the coverage, signal strength, and enhance the spectral energy and boost the secrecy. Now, conclusion as I have discussed, the physical layer security is uh, is a is a physical layer security leverages the wireless medium characteristic to prevent the eavesdropping and unauthorized access. So these are used. IRS are used. AIML and cooperative jamming used to enhance the adaptive and dynamic protection of the PLS. At last, I would like to say that by combining these methods, create a multi-layered intelligent physical security framework for future 6G system. Thank you.
Yeah, so it was like a study of 6G technology, right?
Yes, ma'am. This is a review paper.
Yeah, it's a review paper. Good, good. Yeah. Just now you mentioned about cooperative jamming. So how it is different from artificial noise generation?
Ma'am, in artificial noise generation, we are using uh, uh, the algorithms.
Mm-hmm.
And in jamming, we are using the jamming process.
Okay. Okay. Then what is the role of friendly jammer?
Well, friendly jammer is it will jam the eavesdropper uh, signal, and it will allow the signal to the uh, receiver.
Fine. Okay. Thank you.
Okay.
Thank you, ma'am. Now we will go on with the next presentation. Soham Mehtre, you're ready with your presentation, right?
Just to enable with sharing the screen because in the share option I'm not able to again. I mean, it was visible, but it's not now.
Okay, what we can do is you can share me the PPT in the chat box, then I'll share on your behalf. So you just tell me when you
Okay.
want to change the slides.
Okay. Just a second. I'll share it.
Okay.
Just a second.
Yes.
I have shared it in the chat box. So will you please present it?
Yes, sure. Just give me a second.
Yeah.
Okay, can you see my screen now?
It's loading.
Okay.
Yeah, it's visible. Thank you so much, Siddhi, and sorry for the inconvenience. So, good morning, everyone. My name is Soham Mehtre, and our project is an IoT-based smart irrigation and plant disease detection using machine learning. And I have developed this project with my team members as displayed. Will you please move on to the next slide, please? So this is the index. I'll be presenting with the abstract, introduction, literature reviews, the research gaps that we have identified in the research, the proposed methodology, the results of the proposed system, and the conclusion and comparative analysis. Please move on to the next slide. So all in all, thinking of agriculture in India, the main problems, the main challenges faced by farmers is inefficient use of pesticides as well as water resources. So what we have done is we have created an IoT-enabled smart plant health monitoring system wherein everything is automated. Like the irrigation systems are automated based on the soil moisture levels, and also an ESP32 cam module is used to continuously click images of plants to detect pests and diseases as well. So all in all, we have tried to solve this problem using automation and machine learning. Please, next slide. As I said before, agriculture is a key economic sector in all developing nations, including India, wherein crop productivity is always adversely affected by the water stress and plant diseases. The current smart agricultural systems do integrate some of the technological parts, but they lack integration, and they treat every part of the plant growth system as an individual standalone system, and there is not a complete system that provides a complete solution for plant health monitoring and irrigations. So we have proposed a system which integrates the soil moisture based irrigation with the CNN based plant disease detection and a low cost embedded hardware. Next slide, please. So these are the papers that we have researched, and among the many more. And as discussed before, some of the problems that we have, or the limitations, or the research gaps that we have identified, is generally there is the system exists as an independent irrigation system, or it provides only alerts based on the current soil moisture levels, or they lack the integration of disease detection, or only standalone disease detection modules are present. So all in all, we have tried to combine these together and create a complete system for completely automated system for disease detection and plant irrigation as well. Next slide, please. So yeah, just as discussed just now, these are the research gaps that we have identified. Uh, Also, the main research gap here is the disease detection models, as they are standalone. They use very heavyweight machine learning models, which require very high quality GPU systems to execute it on them. So, using lightweight CNN models, we have curbed this need to have large scale machine learning hardware, wherein large computational power is required. So we have all in all just reduced the required computational power by using a lightweight CNN model. Next slide, please. So this is the proposed methodology in which we have Arduino Uno module, which controls all the sensors. A soil moisture sensor is present in the plant soil near the roots, and it gets all the soil moisture levels. A DHT11 sensor reads the temperature and the humidity in the environment. Why have we used this? Because the evapotranspiration values in the environment contribute to more contribute to the amount of evaporated water content from the plant. So based on this evapotranspiration value, the thresholds for irrigation can be increased or decreased. So in summers, the plant will get more water, and in winters, it will be comparatively less water. So we have used DHT11 sensors and integrated evapotranspiration values as well. Arduino Uno controls all the systems and these sensors. A relay and pump mechanism is used, wherein if the moisture level is below a threshold, the relay automatically turns on the pump for irrigation. And a flask backend is present, wherein a disease detection CNN model and a pest detection CNN model is present. The ESP32 cam module is used to continuously click images of the plant for every 30 seconds, and these images are then transferred into the models for evaluation, and they either evaluate it for the specific diseases. And then a recommendation engine, the model provides some recommendations based on the detected diseases and the detected pests, wherein the user can use those suggestions to uh, uh, take care of the plant, wherein the specified pests or the specified diseases can be get rid of. And a Streamlit dashboard is present, wherein all the information is provided to the user. So all in all, an automatic control is also present, and also the user can shift to manual control, wherein the user himself or herself can control the system according to the need. Next slide, please. This is a photo of the implemented system and hardware, and we have successfully integrated this is a prototype actually. So we have successfully integrated all the sensors and the plant-based monitoring system. And the main part of this is it has automatic triggering, it has real-time soil integration, and it is very low cost and compact design. So it has a reliable field operation wherein continuous operation without manual intervention or hardware failure can be done in this system, as it is a very small scale system. And yeah, all in all, it's a very cost-effective model. Next slide, please. So this is the dashboard wherein all the information related to the plant. We have used the rose plant for testing here. So the as the dashboard presents, the soil station, the live soil moisture status was 62%, confirming the accurate readings. The disease detection output was accurate it gave a black spot disease as an output, wherein the rose did have a black spot disease. Pest detection accuracy was great as there were no pests present and the model read it as no pest presence. Automatic irrigation status is the remains on standby because the moisture levels were accurate at that time. And the clear visualization of those suggestions as well as the correct information of the plant and the click photos as well are provided in the dashboard itself. So the user can look at the dashboard and get clarity in decision making rather to take care of those plants. Uh, Next slide, please. So this is the comparative analysis of the existing systems and our current system. As I mentioned before, we tried to solve those problems that were present in the current implemented methods, like combining all those standalone systems together and creating a complete solution for plant health monitoring, and which helps for the farmers and even the gardeners or small scale home farmers to take care of their plants. And the absolute need for large scale hardware resources is curbed by using lightweight CNN models. Next slide, please. So all in all, to conclude, this complete solution is very scalable. As in, if in future we can scale it to large scale farming as well, we can include drone imaging as well to get images of large scale farms, and analyze the amount of water requirements as well as the efficient irrigation management. And also we can include multiple cameras in specific areas in the farms wherein it gets continuously gets photos of those plants, and then we can identify the disease and pests for large scale farming as well. So all in all, this project is very much scalable and very much efficient for future use on large and as well as small scales. Thank you so much.
Thank you. Great to see your results and your actual work. Now, can you tell me how does this security challenges are overcome in IoT based plant monitoring?
As of now, ma'am, we haven't encountered any security challenges in the present system, but I'll surely look into it. I mean, what are the challenges and what can be the solution for them?
Okay. Are you using cloud to store your data somewhere?
Uh, Not yet. We have planned on using cloud. That is, on large scale farms, we can use cloud systems. The wireless sensors can be used and a WSN can be created, wherein the data will be directly transferred to the cloud storages and the cloud computing modules in
Yes,
AWS.
since you created a dashboard, so I thought that you might be using cloud to store the data and to analyze the data.
Not yet, ma'am, but we can integrate it. Yes.
Yes. Okay. Thank you. Thank you.
Thank you so much.
Thank you for your presentation, sir. Now we will go on to the next presenter. The next presenter is Christian Cornel Gurio from Universidad de las Fuerzas Armadas, ESPE. And the paper title is Proposal of a Web-based Platform for Estimating Planting Density in Cocoa Crops Using Photomagrammetry. So you can start with your presentation. Hello. Is anyone from this particular paper title present?
Can you view the presentation?
Yes.
Good morning, everyone. Thank you for being here today. My name is John Cruz from the Universidad de las Fuerzas Armadas ESPE, and it is a pleasure to present our research entitled Proposal of a Web-Based Platform for Estimating Planting Density in Cocoa Crops using Photogrammetry. Introduction and motivation. I would like to begin by briefly explaining why this topic matters. Cocoa is one of the most valuable agricultural products in Latin America. Beyond its cultural importance, it is also a major contributor to the international chocolate industry and the economies of producing countries. For many small and medium-sized farmers, cocoa production is their primary source of income. Because of this, the ability to monitor and manage cocoa plantations efficiently becomes essential. One key variable in plantation management is planting density. Planting density influences almost every agronomic decision, from estimating yield potential to planning pruning cycles, managing shade, and even forecasting future productivity. Incorrect density measurements can lead to poor field decisions, misallocation of labor, and significant economic losses. Traditionally, the process for estimating planting density relies heavily on manual labor. First, technicians need to physically walk through the plantations, then visually identify each plant, count them one by one, and finally then record the results manually. This method is not only slow and exhausting, but also highly susceptible to human error. Fatigue, terrain conditions, and vegetation complexity can all affect accuracy. At the same time, precision agriculture is rapidly evolving. Modern agricultural professionals expect tools that allow them to work more efficiently, make data-driven decisions, and reduce manual workload. That is the main motivation behind our work. We sought to design a solution that brings automation, accuracy, and accessibility together in a single platform. Our research addresses this need by developing an intuitive web-based platform that uses aerial images captured by drones and computer vision algorithms to automatically detect cocoa plants and calculate planting density with high precision. This combination of photogrammetry and artificial intelligence allows us to turn what used to be a tedious manual task into a fast and reliable digital process. Problem description. The problem we tackle is the challenge of performing accurate and scalable density estimation in cocoa plantations. Cocoa presents unique difficulties when compared to other crops. Unlike open field crops, where plants are clearly separated, cocoa trees grow under shade, often surrounded by taller vegetation. The canopy is irregular and leaves from one plant can easily overlap with those from another. In practice, this results in a series of challenges. The crop grows under shade, which means lighting conditions vary drastically across the plantation. Leaves frequently overlap, hiding parts of the plant from aerial view. Young sprouts may grow extremely close to the mother plant, creating clusters that are hard to distinguish. And perhaps most importantly, there are no standardized datasets for cocoa detection, which makes training AI models more complex. These factors make automated detection significantly harder. Shadows, occlusions, changes in illumination, and variation in plant growth stages all influence the performance of computer vision models. Therefore, designing a reliable system requires not only good imagery, but also careful model training and software integration. Proposed solution. Our proposed solution is a fully integrated workflow that connects four major components. First, drone-based photogrammetry provides high-quality images of the plantation. Second, an AI-driven detection pipeline powered by YOLOv8 analyzes the images and identifies each cocoa plant. Third, a web platform processes the images, displays the results, and manages user interactions. And fourth, a database stores historical records, metadata, detections, and density values. The goal is not just to count the plants. The goal is to offer a practical, accessible tool that supports real decision-making in the field. By reducing the time required for monitoring and making results more consistent, the platform contributes to more efficient and sustainable agricultural practices. Methodology data acquisition. Let me now describe our methodology. We collected high-resolution aerial images using a DJI Phantom 4 Pro drone. This drone allows us to capture detailed imagery at different altitudes while maintaining good clarity and color balance. The final dataset consists of approximately 3,000 images collected across different plots, altitudes, and even different seasons. This variety is essential because it helps the model learn to generalize across different lighting conditions, canopy structures, and plant sizes. Dataset preparation. Once the images were collected, we used RoboFlow for dataset preparation. RoboFlow allowed us to label each cocoa plant manually and organize the dataset effectively. We also applied augmentation strategies such as rotation, exposure adjustments, and simulated blur. These augmentations help increase robustness because the model must learn to detect plants even when the images are not ideal. Model selection and training. In the model selection phase, we evaluated several object detection architectures, including older YOLO versions and other competitive models. YOLO 8 offered the best balance between accuracy, computational efficiency, and processing speed. It was therefore selected as the core detection model. We trained the model for 150 epochs using a batch size of 16 and an input resolution of 640 by 640 pixels. Throughout training, we monitored performance using Comet, which provided real-time insights into accuracy, recall, loss curves, and GPU utilization. This monitoring allowed us to adjust parameters and ensure the model improved consistently. Software architecture. For system implementation, the platform follows a monolithic layered architecture deployed on Google Compute Engine. The frontend was developed using Angular, chosen for its modularity and clean component structure. This allows technicians, even those without technical backgrounds, to navigate the interface easily. The backend was built in Python using FastAPI. FastAPI offers excellent performance and integrates well with machine learning workflows. It handles image processing requests, loads the trained model, and executes the detection tasks. We used MySQL as the database engine. It stores metadata about the images, the detection results, and all the density calculations. Thanks to this structure, users can track historical data, compare results across time, and maintain a detailed record of plantation evolution. User workflow. The user workflow is intentionally simple. A technician logs into the platform, selects an aerial image, and uploads it. The backend processes the image using the YOLO 8 model, identifies the cocoa plants, and generates bounding boxes around each detection. The system then calculates a numeric density value and returns both the annotated image and the analysis results through the web interface. The user can review the data, download the outputs, or store them for future reference. Results. The performance results were highly promising. The model achieved around 95% accuracy in detecting cocoa plants. More importantly, when compared to manual field counts, the system maintained an
Hello.
error margin.
Sir, sorry
This
for the interruption, but we are past the presentation time. Could you please get to the conclusion? Hello.
To summarize, we successfully developed a web-based platform capable of automating cocoa density estimation using photogrammetry and artificial intelligence. The system reduces monitoring time, minimizes human error, and provides technicians with reliable data for decision-making. With accuracy near 95%, the platform demonstrates strong potential for agricultural use and contributes to the development of precision agriculture tools. Thank you.
Yeah, it was a great presentation and great work. And I'm really new to this photogrammetry term. Yeah. Yeah. Can you tell me what kind of loss function is used in yellow? Hello. Hello. Sir, am I audible to you?
Yes, ma'am, you are audible. I think he's not able to hear. Maybe.
Available several YOLO variants. YOLO version 8 was selected because it demonstrates superior detection accuracy and higher computational efficiency compared by version 5 or 7. This is crucial for high performance detection in the backend.
Okay. Okay. Yeah. Yeah. Thank you. Thank you.
Thank you. So now we'll go on to the next presenter.
Thank you.
So the next presentation is by Ritika Valinayagam from Sastra Deemed University. And the paper title is Robust Speaker Authentication System Against Replay Attacks, Perceptual Features and Models. Ma'am, please start with your presentation.
Yes, ma'am. Is my presentation visible, ma'am?
Yes.
Okay, ma'am.
Yeah, it's visible. Yeah, continue.
So, good morning, everyone. Today, I, Ritika, along with my team, Geetika and Pranay, are going to present a research paper on speaker authentication system against replay attacks under the guidance of Dr. Revati. In today's digital world, keeping our data safe is really important. Many systems use use biometrics like fingerprints or face scans, but these often need special and costly devices. An easier option is voice-based authentication. It simply needs a microphone and a computer. But there is a problem. Voice systems can be tricked using replay attacks. In a replay attack, someone records a person's voice and plays it back later to fool the system. This kind of trick can break the security of voice authentication. So, in our research, we aim to build a strong authentication system that can not only recognize the right person by their voice, but can also detect and block replayed or fake voices. This helps make voice-based security more reliable and safer to use. So in our project, we have used the AVS Spoof database. This has been specially designed to evaluate the robustness of speaker verification system. The database includes both genuine and replayed recordings. We have selected 10 speakers, 5 male and 5 female speakers to work with. We have used 3 types of replay attacks, which are laptop, phone 1 and phone 2. So the first step is feature extraction. Here we'll extract the PLP features. So the process begins with loading the input signal and then it is pre-processed to reduce the noise, boost important frequencies and divide it into smaller frames. Each frame is then converted into the frequency domain to obtain the power spectrum. The power spectrum shows how the energy is distributed across different frequencies. This spectrum is filtered using Bark or Mel scale filters so that it matches the human hearing. Next, perceptual scaling and nonlinear compression is applied to adjust the signal according to how the sounds are perceived. The processed signal is then converted back to time domain. Linear predictive modeling is applied and the resulting LPC coefficients are transformed into substral coefficients. These final values form the perceptual linear prediction features, which stand for PLP, which are compact, stable, and widely used in speech and speaker recognition systems. Next step is modeling. Here K-means clustering method is used. The goal of K-means is to help the system to tell the difference between real voices and replayed voices by studying the way these features are spread out in the data. First, we load the PLP features. The features vary in scale and range. Therefore, normalization is applied to the PLP features to equalize the data set and ensure uniformity. Once the data is normalized, we use K-means algorithm to divide the features into K clusters. Each cluster groups together similar patterns in the speech data. The center of each cluster is called centroid and it represents the key characteristics of that group of features. Instead of storing all the voice data, the system just stores these centroids. This makes it easy to save and use. The final step is testing. It starts with loading the PLPs of the test signal. These features are then normalized to ensure uniformity. Next, the signal is segmented into overlapping frames. The system then loads pre-computed cluster centers that represent genuine speakers. Now, for each frame of the test signal, the minimum distance to all cluster centers is computed. Based on this, the frame is assigned to the closest cluster, effectively identifying which speaker it most likely belongs to. This assignment helps in identifying the speaker, and the system then evaluates the performance by generating a confusion matrix. So this is the confusion matrix for genuine versus genuine signal. Here we are comparing the audios of the real speaker. So the diagonal values of the matrix are comparatively higher than the non-diagonal elements. Higher value of diagonal element indicates that the test audio and reference audio are similar. The acceptance rate for speaker 6 is low, so correlation is done for speaker 6. The correlation coefficients obtained are negative. So this shows that there is low similarity and thus the accuracy is low. This is the confusion matrix for genuine versus replay laptop signal. Here we are comparing the real signal with the replayed signal. So the accuracy along the diagonal of the matrix is comparatively lower than the non-diagonal elements. For speaker 10, the accuracy is comparatively higher. So we performed correlation and the coefficient value obtained was positive, which shows there is higher similarity between the signals and thus the accuracy for speaker 10 is high. This is the confusion matrix for genuine versus replay phone 1 signals. And this is the confusion matrix for genuine versus replay phone 2 signals. Here we have done the performance evaluation where the accuracy for each speaker at different cases has been plotted in the form of a graph. So the speaker authentication system can be used in a wide range of real world situations such as banking, forensic investigation, financial services, and more. So to conclude, I would like to say that the system could accurately differentiate between the real speech and the replayed speech. So by using proper feature extraction technique and modeling technique, we can generate a speaker authentication system that are more secure and reliable. These are the references used. I would like to thank everyone for giving us this wonderful opportunity. Thank you.
Yeah, one question from my side. There are
Yes,
two
ma'am.
types of replay attack, online and offline. So can you differentiate between these two or both are same?
Actually, we have used the already recorded voices for this case, ma'am. We have not used it like online and offline. So,
Okay. In the cryptography, we use hash function, right? So how this hash function will prevent the replay attack?
we have not used any concept like hash function and all in this, ma'am.
Mm-hmm. Okay.
Yes, ma'am.
Okay. Thank you. Thank you.
Thank you, ma'am.
Thank you, ma'am, for your presentation. Now let's move on to the next presenter. So the very last presenter of today's conference is Bharati, ma'am, from Arignar Anna Government Arts College, and the paper title is Mode K means WO, a hybrid ensemble framework for student performance prediction. Ma'am, please start with your presentation.
Yes, ma'am. Yes, ma'am. Is it visible, ma'am?
No, ma'am, you haven't shared your screen. Ma'am, is there any issue?
Yes, ma'am.
Ma'am, your screen is visible now. You can start with your presentation.
Yes, ma'am. Is it visible, ma'am?
Yes.
Yes. Good morning to all. I am Bharati, research scholar. I am pursuing PhD. My presentation is entitled on Smart K-means WO, a hybrid ensemble framework for students' performance prediction. Outline of my presentation is abstract introduction, related work, proposed computational model, experimental analysis and discussion, and finally conclusion. My study proposes a novel ensemble framework that combines three advanced techniques to predict students' academic performance with enhanced accuracy and robustness. The framework integrates SMART for addressing class imbalance inherent in educational dataset, WO for intelligently initializing K-means centroids, and K-means clustering to segment the student population into meaningful groups. The optimized cluster assignment feed into ensemble model such as CAT-Boost, LightGBM, and XGBoost for student performance prediction. The proposed model's predictive performance is evaluated over two standard students' performance data set, and its efficacy is benchmarked against the state-of-art methods. The existing students' performance prediction systems suffer from key limitations that hinder their effectiveness in real-world educational settings. To overcome this limitation, we need some intelligent techniques. The proposed model addresses this limitation by incorporating advanced ensemble methods, SMART K-means WO, to predict student performance. The articles are downloaded from various data sources such as IEEE, Springer, Google Scholar, etc. Some of the review articles shown here. In 2022, Mustafa et al. Applied random forest neural network support vector machines to predict student performance. The dataset contains 376 students from UCA machine learning repository. The random forest yield 74.6% of accuracy. In 2022, Fidila et al. Implemented decision tree, K nearest neighbor, random forest, linear logistic regression support vector mission for student performance prediction. The University of California Irvine open access student dataset was used to evaluate the model. The random forest achieved the highest accuracy of 94.9%. This is the architecture of my proposed system. The data is given as input to the system. The synthetic minority oversampling technique SMOT is applied to address the imbalanced nature of the dataset in stage 1. In the next stage, the K-means clustering algorithm is applied over the pre-processed dataset. The K-means group feature clusters based on the cluster size. The drawback of the SMOT K-means technique is that the random initialization of K-means clustering produces inconsistent features into different clusters and fall into local minima problem. This issue is overcome by hybridizing the K-means clustering with the Walrus optimization to find optimal initial centroid. So this technique is referred as SMOT K-means WO for student performance prediction. In stage 3, these features are fed into 3 ensemble classifiers such as CAT-Boost, LightGBM, and XGBoost for student performance prediction. Finally, the performance of the proposed model is evaluated with 2 benchmark dataset, XAPI Edge data and student MAT dataset. The reason to choose SMOT for data balancing is that I have conducted a comparative analysis of data balancing techniques. I found that the SMOT is the optimal choice for educational dataset based on multiple criteria. The reason to choose K-means clustering is that because of its base quality, computation efficiency, and education data characteristics favor the K-means, I have chosen K-means for clustering. The reason to choose Walrus optimization is that it excels over other meta-heuristic optimization algorithm due to superior global exploration and avoiding premature convergence and local optimal traps common found in clustering tabs. I have chosen the XBoost, LightGBM, and CATBoost for classification because of its industry standard based accuracy and excellent feature interaction. And I have chosen the XAPI Edge data and the student math dataset because of its rich features and established use in research. The studied algorithms are implemented using the software MATLAB. The gradient boosting classifiers such as CATBoost are originally developed in Python. These libraries are utilized in the MATLAB environment by accessing Python functions using MATLAB external interface. The two benchmark dataset XAP Edge data and the student math UCA dataset are used to measure the performance of the proposed algorithm. The XAP Edge data consists of 480 instances and 17 attributes. The student math dataset consists 395 instances with 33 attributes. The SMOD pre-processed dataset contains 1414 instances, and the SMOD student math dataset consists of 2631 instances. Among these, 80 is utilized for training and 20 is taken for testing. The accuracy is used as evaluation matrix, which is calculated as a ratio between the number of student records correctly classified and the total number of students records. The table presents the experimental results of SMOD K-means with Ensemble classification accuracy. The experimental analysis of SMOD K-means approach demonstrates significant improvement in the clustering effectiveness. In run 1, the 8 features 18 to 15 in cluster 1 are fed into the CATBoost, LightGBM, and XGBoost classifiers and achieve the highest accuracy of 88.3%, 85.82%, and 87.23% respectively. In run 2, the 12 features in cluster 2 resulting in accuracies above 87% across all classifiers. In run 3, cluster 1 contains 8 features that outperformed other clusters. The CATBoost yielded the highest accuracy of 89.01 for cluster 1. This table presents the experiment results of SMOD K-means with Ensemble classification accuracy. Each execution of SMOD K-means approaches yield a different set of features, which reduces model stability. To overcome this issue, the SMOD K-means approach is integrated with the Walters optimization technique to select the optimal initial center for clustering. The cluster 3 combines F2, F3,
Hello.
F9.
Sorry for the interruption, but we are
Yes.
past the presentation time. Can you
Oh.
please get to the conclusion?
Yes. Yes, this is the final result. The cluster 3 with only 8 features such as F7 to F11, F24, F31, 32 yielded the highest classification accuracy of 94.68%. SMOD K means with W gives 95.25%, which is higher than all the state-of-art methods. The proposed novel hybrid ensemble framework that combines 3 advanced techniques to predict students' academic performance with enhanced accuracy and robustness. So my framework enables early intervention system of identifying struggling students at early and allowing educators to provide targeted academic support and improve students and institution retention. So that's all my. Thank you. These are all the references I have referred for my study. Thank you. Thank you.
Yeah, ma'am. Great to see your work. There are 3 types of SMOD, borderline SMOD, and SMOD K-means.
Yes.
So why you have not prefer borderline SMOD?
So I conducted a comparative analysis of different balancing techniques. I found that a SMOD is the optimal choice for my study. That's why I have chosen a SMOD technique, madam.
Okay. Then how this SMOD K-means handle overlapping classes?
So the optimization, Walrus optimization used to resolve this kind of problem, madam.
Okay. Thank you. Thank you,
Thank you, madam. Thank you.
Yeah. Thank you.
Thank you, ma'am. Thank you. This is the last presentation. Now we just have a few instructions. First of all, I sincerely thank our authors for their excellent presentations and contributions in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for your support during the 10th version and all the previous 8 versions of the conference. We will be happy to have you in the 11th version in 2026. All the presenters will be getting their digital certificates via email within 2 working days, and the publication will be live within 7 to 8 months. Kindly cooperate with the team of ICTCS 2025. I also thank our session chair, ma'am, Vidya ma'am, for chairing this session.
Yeah, thank you, Siddhi. Yeah, thank you.
A token of appreciation to the chair on behalf of Team ICTCS and Global Knowledge Research Foundation and partners.
Yeah,
Thank you, ma'am, for your valuable presence.
yeah, thank you. Thank you.
Now, before ending this session, I would like to request all of you to please switch on your cameras so that I can take a quick snapshot of today's virtual session. We'll just wait for a few seconds for everyone to turn on their cameras and then I'll take the shot. Okay, I've taken the snapshot. Thank you, everyone. This was a great session. Now you all may leave the meeting.
Yeah, thank you, Siddhi. Yeah, thank you.
Thank you.
Thank you.